Hey folks, today I'm going to be talking about some basic information that you're going to need to be able to solve our group's homework problems. It's kind of prerequisite information that was covered by the previous group that we feel that you could probably use some more information on to help you better understand our group's problems. We're going to be walking you through how to solve a basic problem involving computing a posterior distribution from a bunch of given information, and step you through it so you can develop an intuition about what you should do to deal with all of these various distributions and vocabulary. So I'll go ahead and set up the problem for you. The goal of the problem is to develop a posterior distribution for the number of birds on a particular signpost. Some of our given information is that we're assuming that the number of birds on this signpost is binomially distributed with n equals 5 and p equals capital P, or capital P is a random variable. The reason I've selected a binomial distribution is because it's reasonable to assume that the signpost only has so much physical space, so maybe only 5 birds can fit on it, and each bird independently chooses whether or not they want to sit on the signpost at any given time. So binomial distribution is a perfectly reasonable assumption for our model distribution. And our next piece of given information is that we're assuming that capital P has a prior distribution 2p to the 4th for values of p between 0 and 1, because p is a probability it has to take on values between 0 and 1. What we're going to do with this prior distribution in developing our posterior distribution is we're going to take in these observations here, and we're going to use them to kind of tweak and update our current assumption about what the prior distribution is into a more accurate distribution for p. The way we developed this current one is purely subjective. I didn't use any particular logic to develop 2p to the 4th beyond it just being easy to calculate. But honestly, this is usually in practice based off of an educated guess. Even then, it's not very educated, because the purpose of doing this problem is to kind of start with an uneducated guess and use observations to update your guess into an educated posterior distribution. So we're just going to be starting with 2p4 for now. We'll be updating that. And as I've already mentioned, here are our 3 observations. We observe 5 birds on Sunday, 1 bird on Monday, 4 birds on Tuesday. And so we'll go ahead in a moment and look at what we need to do to our prior distribution to incorporate these observations and make it more accurate. We start by defining our prior distribution given to us in the problem. Usually the prior distribution is denoted pi of whatever parameter you're trying to predict. And we define the problem as 2p to the 4th, or p between 0 and 1. And intuitively you can think of this as just the probability of some event A, where A is p takes on a particular value. And next we define our model, or our likelihood function, same thing. And we define it as f of x given p equals the binomial distribution for our predicted number of birds that sit on that signpost. So we gave you that n equals 5 and that p is unknown random based on our prior distribution. And that intuitively you can think of as the probability sum of it b given that a occurs, where b is the number of birds and a is the parameter value p taking on a value. And then we have to incorporate our observations to start updating our prior distribution. So we have our 5, our 1, and our 4. If you'll notice from our prior distribution, because it's 2p to the 4th, larger values of p are being given a lot more weight than smaller values. So since we have this 1 in there, what the effect that's probably going to ultimately have is drive down our posterior distribution as far as how much weight it gives to values. It's probably going to end up giving more weight to lower values as a result of that 1 that gets stuck in there. But proceeding, we go ahead and start calculating our joint distribution, which is just the product of the prior distribution and the product of the final value of each likelihood function when you plug in each of these observations. The final formula that you get out of that is 50 p to the 14 minus p to the 5th. You can think of that intuitively as just taking our likelihood function, but plugging in each value of our observation and multiplying those together, and multiplying those by our prior distribution. Then we go ahead and calculate our marginal distribution, which is just the joint which is just integrating over the joint distribution with respect to p. And the final number you get out is this really tiny constant over here. The reason we're computing a marginal distribution is because it always gets out a constant, and so that when we take the joint distribution and divide it by that constant, it'll normalize the joint distribution into a legitimate probability function that integrates to 1. If you'll remember, if you notice, our current prior distribution does not integrate to 1 over its range. but the posterior distribution has to if we want it to be useful. Because this was just a guess. We never planned to use this practically, but we will do that for the posterior distribution. So we get this number, and you can think of it as just the probability that B occurs given all possible values of P or A, so it's going to be a constant. And finally, we can actually calculate our posterior distribution. This is usually denoted pi of our parameter given each of our observations, and it's calculated simply as our joint distribution divided by our marginal distribution. And the final value is this crazy number right here, 232,560 times p to the 14 times 1 minus p to the 5th. This is our final distribution that we use. This is based on our observations, is our most accurate guess of what possible values p can take on, what probability those values have coming up in the population. All right, so this is just to provide a quick graphical illustration of why Bayesian estimation makes our guesses about random events more accurate. As you can see, our prior distribution has a very unreasonable probability distribution function, even though it's not technically a proper one because it doesn't integrate to 1. But what it does do is give just crazy weight to values of p close to 1 compared to other values. Then when we take in our 3 observations of 5, 1, and 4, especially that value of 1, which drives down the weights that the prior distribution would give to the p-values, it creates this distribution which lumps most of the probability around the 5 and the 4 that we observed. So that makes intuitive sense. You can see why, based on these 2 graphs and what the observations do to our estimations of the true distribution of p, why Bayesian estimation is useful for just updating random guessing to something more educated.